Okay, so Osmocom in the year 2020. Try to give it a little bit of structure. As I said, I have a couple of bullet points, no formal slides. I will scroll through the bullet points and talk a bit about it. In terms of like general topics that didn't really fit into any specific sub-project, there are a couple of things I found worth mentioning. We had one large extension of the VTY, our command line interface, where now it is their attributes, and every command tells you when the respective setting becomes active, because some of the settings become active immediately, some others require full process restart, others only become effective once a given peer, let's say a BTS, is reconnecting, and so on. All of this is now, thanks to Vadim, is now documented in the VTY, and you can interactively explore it on the VTY. We have we have multiple new Osmocom programs with acronyms as usual. So we have Osmo SMLC, the Serving Mobile Location Center, which is an element of the location services framework in 3GPP. And using an SMLC, or rather, let's say the core network can obtain a more detailed position of the mobile station, for example, in case of an emergency call. The SMLC talks to the BSC, and the BSC has been extended accordingly, which we will talk about slightly later. There's another new program in the Osmocom universe called Osmo UE Cups. That's the user equipment control user plane separation. Control and user plane separation cups is something that has been happening a lot in the domain of the PGW or GGSN in the last decade or so, which means that you don't have the control and user plane in one network element, but you split it between two. And Osmo UE Cups is basically something like that, but for the user equipment side. And you can use it to emulate user equipment towards a PGW or GGSN. There's a control interface by which you can basically tell it, well, create a GTP tunnel from the, let's say, UE side. It then emulates the SGSN or the SGW. And you can tell it, well, for the PDP context, which has an IP address and so on, create a new network namespace and start this or that program inside. So you can use this as like an engine that will create network namespaces that emulate a given user equipment towards the core network in the packet switch domain for both 2G, 3G, and 4G. It is used by some of the TTC and 3 tests that we have for testing PGWs. Then we have support for so-called radio information messaging and network-assisted cell change. That's an optimization of the 2G packet switch domain in the PCU and the SGSN and GB proxy. All of these network elements need to support it. The idea of this is that, first of all, RIM means there is a way how individual PCUs can exchange messages with each other. Normally, the classic 3GPP architecture is strictly hierarchical, and there's no communication, like, let's say, within one level or layer of the network between PCUs, but a PCU talks to the SGSN, and the SGSN talks to the GGSN, but it's not a flat architecture. But by means of RIM, PCUs can exchange messages with each other. It's like a packet transport with cell identities as source and destination addresses, and all the elements then route the messages. And using this transport, the NAC, network assisted cell change, can transport system information messages between PCUs, which is useful for faster cell change between cells in the packet switch domain. So it allows you to reduce the latency when switching cells in the packet switch network. Then we now have IPv6 support all over the radio access network, which means specifically the A interface, the GB interface, the IU interface, the LB interface, that's the SMLC interface, also MGCP. So basically IPv6 everywhere in the radio access network with the exception of ABIS and not in the core network elements, at least not on all interfaces yet. We also have real-time scheduler configuration now in the VTY. So every program, if it enables it, can the real-time scheduler priority can be configured via config file or the VTY. We also, in addition to the Debian and Ubuntu packages, we now have RPM packages. Spec files have been put into all of the CNI projects, and we have an OBS build for CentOS 7 or 8.
8.
8, yeah. So 7 is wrong there. It's CentOS 8. But of course, it would be easy to also build for other distributions. I mean, the important part is that we have spec files now. Okay, looking a bit at the individual radio access network elements first. Osmo BTS, one of the major changes is we have base station power control, which means power control in the downlink. This you want to have for two reasons. A, to reduce power consumption at the base station. B, to reduce downlink interference with neighbor cells. Since there's frequency reuse, every couple of cells, the same frequency is used again. Excuse me. You will create cells will interfere with each other. And of course, if they transmit less power, there's less of a chance of interference. Excuse me. We also have support for baseband frequency hopping in the BTS now. We never had that before. That's definitely a new feature. Vadim has been working on this mainly. Well, why do you want frequency hopping? I mean, it's mainly a policy decision, but the main advantage of frequency hopping is, of course, avoiding interference and equaling mitigating effects of narrowband interference because you hop over multiple frequencies. We have tons of fixes regarding measurement reports. It's of course not reports regarding, but bug reports regarding measurement reports and corresponding fixes. We now have filtering of power control loops, which avoids oscillations in power control, both uplink and downlink. And we have two rather modern GSM features, which is called repeated downlink and uplink fetch. Actually, we also have repeated fetch, which are really 6 features. It's actually quite interesting to read about those. I probably could talk 45 minutes just about those and why it's such an interesting development, but I have to skip that, unfortunately. Basically, these features allow you to extend cell coverage in situations where your carrier to interference ratio is really bad. But still sufficient for an AMR call, but the signaling would otherwise break down if you don't have those features. So you can extend the usable cell radius using those features. In Osmo TRX, we now have a couple of measured default calibration values to get a more realistic RSSI. This gets back to the general problem that all of the general purpose SDRs like USRP, B210 or Lime SDR or whatever you want to use, they don't have any like calibration tables on board. So if you receive a signal, you get an indication like how many dB full scale that might be, but you don't really know what full scale is, and you don't really know what is the absolute received signal level at the input port of the device. But these absolute levels are what's used in GSM everywhere. So what we took is we took a couple of measurements with 2-3 boards in different bands and put that hard-coded in the source code. So at least we have some realistic values rather than none at all. It's of course far from being a calibrated device, because a calibration means you have a device individual calibration just for your specific device. That is nothing that we can, of course, create, but at least we can have some defaults that are not too far off based on our experience. We have some Prbs related tools. So Prbs is pseudo-random bit sequences. Those are required for bit error rate testing. So using that, you can make OsmoTRX transmit such sequences, including simulated bit errors. We have a new OsmoTRX backend. So in addition to OsmoTRX UHD, OsmoTRX LMS, and OsmoTRX USRP1, we now have OsmoTRX IPC. IPC means inter-process communication, and rather than talking to a specific driver like UHD, it implements a documented shared memory interface. And on the other side, let's say on the lower side of that interface, you can plug whatever hardware you want. One reference implementation has been published, which again uses UHD, so it doesn't really give you any advantage. But of course, there may be other hardware that you can plug into OsmoTRX using this generic shared memory interface. Shared memory, of course, to avoid copying all the samples again and again, so the samples can just go zero copy through the shared memory. We also now have proper transmit amplitude scaling. There was a mistake in power versus voltage scaling. So if you said, I want to reduce by 2 dB, and that was not correctly implemented, it's now fixed. Of course, there were tons of other changes, but these are sort of the ones that I thought were important, or particularly important in terms of the PCU. Lots of fixes, particularly in the CSN1 encoder, decoder. Fixes for passing the mobile station radio access capability. We had some encoder bugs in the paging request, embarrassingly, so I don't really know how that could ever have worked. We have various other fixes here and there. Probably not go through all of them in detail. We have IPv6 Nsvc support now, as I mentioned before, big topic. Also, frequency hopping, of course, had to be added to the PCU. Doesn't make sense if it's only supported by the BTS. Both have to support it. We now downgrade the downlink coding scheme in GPRS-only mobile stations, and so on. I think one of the major topics really is that line here. In the past, you had to choose whether you operate GPRS or eGPRS. Well, actually, there's one character too many in this acronym. It's eGPRS. And now Power has managed to get the code into a state where it supports both. So you can operate Osmo PCU, and you can have GPRS-only mobile stations in combination with eGPRS-capable mobile stations, and the scheduler will work out to do the right thing, which is slightly complicated, but which goes beyond this talk here. We also support the so-called IP subnetwork service in the GB interface now. That's a way to auto-configure and dynamically configure the endpoints of the GB interface between SGSN and the PCU. We have network-assisted cell change support. I mentioned before in the generic section what that is. It uses RIM to message system information between PCUs, and it allows you to change cells more quickly in 2G cell change on the packet switch domain. A lot of conversion from C++ to C. Osmo PCU has always been sort of a hybrid, some stuff in C, some stuff in C++, and not really nicely done on either side. And so there's some conversion to come to a more unified implementation there, and lots of additional work that Pau could probably speak for an hour about, maybe at another time. Any questions on those elements so far before I proceed? Everyone dead already by now? Maybe try to do this a little bit less detailed. On the BSC side, we have reintroduced proper E1 support, specifically for Ericsson RBS 2000. That's an Ericsson macro base station family. E1 interface support has been in our BSC in the very early days in 2008. we have reintroduced it properly now after many years of not having E1 support in the stack, so it's now fully supported. We have had a bug that if you enabled it as an operator, which is not recommended at all, but if you did so, A52 actually had higher priority than A51, which is a serious problem since A52 is the weaker encryption cipher. We now have support for Msc Pooling. Msc Pooling is also a relatively modern feature by which the BSC doesn't connect only to one MSC, but to multiple MSCs. And there's some resource distribution based on some bits in the TIMZ going on. So some TIMZs are handled by one MSC and some other TIMZs are handled by another MSC. And this approach allows more easier scalability, and it's implemented, I think, in most networks today. So we also had to support that in our BSC. There's a lot of new code for cell broadcast scheduling and supporting the CBSP interface. That's the cell broadcast service protocol by which the core network performs cell broadcast and public warning messages. We have this LB interface for location services that I mentioned in the context of Osmo SMLC. We have lots of frequency hopping related fixes and tests. As I said, well, I didn't say it, sorry. We did support frequency hopping again, like, 10, 12 years ago, but somehow it got lost over time since most of the BTSs we worked with didn't support it in the meantime. Now that we support frequency hopping from Osmo BTS, we had to fix the issues in the BSC as well. Some more circuit switch fallback related fixes regarding encoding of certain parameters. Then we have access control class rotation and access control class ramping. So access control classes are sort of a way how to distinguish different classes of subscribers. The usual approach is that you evenly split all the 14 or whatever it is available access control classes among your subscriber population. So on average, 1/14 of your subscriber base is within one access control class. And in the system information messages, you broadcast a bit mask of which of those access control classes are permitted to even attempt to send a REG request and to register to the cell. What we implemented already several years ago is ACC ramping, so that when a cell comes up, we don't enable all of the access control classes immediately, because that would mean that potentially tens of thousands of subscribers want to register at the same time. But we slowly enable bit by bit more and more access control classes to ramp up the registration load, the location update load. And now we don't only do that ramping when ramping up, but we can also do it as a load control mechanism. If we overload it, we can basically disable some access control classes. And if we disable some, we can then rotate the disabled classes so that it's not only one group of subscribers that can never register, but that sort of all subscribers can register with an equally bad or good probability over time. Lots of more counters and statistics required a lot by operators. They want to see lots of figures in their KPIs, the key performance indicators. So we added quite a number of them, and still there are some more being added. We still have some patches in review even right now. We now support emergency call preemption. That means if emergency calls are enabled and an emergency call is received and all channels are allocated, then some other existing non-emergency call is terminated immediately, and that radio resource is then allocated to the emergency call. Something that's required for regulatory reason in a lot of deployments. We have some improvements on LTE neighbor cell information elements in some of the messages, so you can configure more details there for combined 2G, 4G networks. We have proper finite state machines for the organization and maintenance link managed objects. That means they should have a predictable and understandable behavior now as opposed to before. Lots of handover improvements to tons of new tests for handover scenarios. Actually, there's even lots of infrastructure for handover tests that is now in C in the code, where we simulate all kinds of scenarios and see if the handover algorithm performs the way we expect in a number of different situations. Some fixes on initial AMR mode, the ACCH repetition, there's some function of the VSC in there as well. And we have a neighbor resolution service, which is required for the network-assisted cell change. In Osmo Media Gateway, we now have a control interface, so counters can be inquired. We support IPv6 for the RTP sockets and IPv6 inside the SDP, inside the MGCP, meaning basically everything in the Media Gateway is now IPv6 related, which is of course required since the Media Gateway is handling the media flows from the core network to the radio access network. It doesn't, so we don't only need IPv6 on the signaling side, we also need it on the user plane. Also, we have support for E1 again, is that in the context of supporting E1 BTSs and specifically the Ericsson RBS 6000 family that is now also supporting the user plane, the voice frames, again, or for the first time inside the Media Gateway, actually. Osmo GB Proxy, which is a custom network element that can be used to aggregate multiple GB interfaces, has received basically a complete re-implementation. I don't think there's so much that survived. First of all, the NS, that's the lower layer of the GB interface protocol implementation was completely rewritten to support really everything that's in the spec. I literally think there's almost nothing that we don't support now that's specified, which is uncommon. Normally, we only implement, let's say, the most important bits, and then we grow gradually. Also, the GB proxy itself has received an overall rewrite now with finite state machines and so on. It supports this IP-SNS, this auto-configuration mechanism for the NS protocol. It supports SGSN pooling. Not just supporting SGSN pooling, but you can now have a BSS, meaning PCU and so on, that doesn't support SGSN pooling, put a GB proxy in front of it, and it will implement the pooling towards multiple SGSNs. So you can, let's say, pool enable a non-pool capable radio access network. We also support vintage computing in the form of frame relay. So we can now attach a third-party BSS or PCU that uses frame relay over E1 to the GB proxy, and the GB proxy can then convert that to GB over IP towards the SGSN. So you can use a BSS from the 1990s that is, let's say, release 97, release 99 3GPP, and attach it to a, release 7, release 15, whatever. SGSN on the other hand side, converting by GB proxy. And that brings me to the end of the radio access network, and I somehow have seriously doubts whether anyone is still listening.
I do.
We're not dead.
Okay, not dead yet. Osmo HLR has received what we call distributed GSM or DGSM support. That's a non-3GPP specified extension that Osmocom implements for operating networks in a decentralized, distributed fashion. You could say like a federated or federation of GSM networks that interoperate with each other. There's wiki pages and documentation about it if you're interested. The other bit that was added, it's not really much on the HLR, is support for XOR 3G authentication. That's the algorithm that is specified for test SIM cards. So normal SIM cards will use, let's say, millenage, for example, as the authentication and key agreement algorithm. But so-called test SIMs, which are normally only used in, let's say, conformance testing and so on, they use XOR 3G, which is not a real, let's say, authentication or key derivation algorithm, of course, but it's something that is very predictable and easy for debugging. The interesting bit of having this supported in Osmo HLR is that you can now use eSIMs. So sometimes you have devices with embedded SIMs these days, and you can now register such devices to an Osmocom network if you know how to enable the so-called eSIM test profile. So according to the GSMA eSIM specification, or EU ICC specification to be more precise, every EU ICC, that's the physical chip, needs to support a so-called test profile. And the test profile then will use specified keys and use this XOR3G authentication scheme to register to the network, and that's now supported. Has been tested with some eSIM. On the STP, the switch signaling transfer point, we now support M3A without routing context information element. That's in order to have interoperability with some other implementations. We have IPv6 support now for all the SIGTRAN protocols, and we have implemented the network management and STCP management, meaning that individual network elements and applications connected to Osmo STP will now be notified about the availability or unavailability of certain peers, meaning that, for example, if you're a BSC, you will get notifications when which MSC point code comes up or goes down in terms of is connected to the signaling network or not. Osmo CBC, the Cell Broadcast Center, it was created in 2019, has received a lot of testing since, has now a working REST interface by which you can add or delete broadcast messages, which the CBC then sends to the BSCs over the CBSP protocol. There's a small Python tool, the CBC API tool, which implements the client side of this REST interface. So from the command line, you can then add or delete messages into the CBC and have a quick way of testing it without writing some kind of third-party application that implements this REST interface. On the GGSN, the gateway GPRS serving node, we now have automatic testing with kernel GTP. Some of you may know that Osmo GGSN supports doing the user plane in user space. So basically doing all the user IP encapsulation, decapsulation inside the normal user space application, inside a normal program. But there's an accelerated Linux kernel GTP driver and GTP tunnel driver in the kernel. And it can use that. However, we didn't have automatic testing for that yet, and that has been added now. And we now test with the latest master from Linus Torvalds. We test the netnext tree, which is where networking-related changes get merged before they go into Linus's tree. And also using the latest Debian 10 kernel package and verify that the user plane driver behaves like it's supposed to behave. That's particularly important since there's quite a bit of patches in recent months against this kernel GTP driver for some 5G related use cases. And we want to make sure that it doesn't break our legacy 2G systems. SGSN-EMU, the SGSN emulator has received support for network namespaces, so it can now, so you start it emulates an SGSN, it sets up a PDP context, it emulates sort of a mobile station and everything. And once the IP tunnel comes up, it can put the TUN device into a new network namespace, and you can start some whatever arbitrary software in this network namespace to isolated from your host network stack on your machine. The SGSN has been receiving lots of protocol correctness fixes. We now also support multiple PCUs in one location area code or routing area code, meaning that paging messages need to be broadcast to these different PCUs. We have routing of RIM messages, again related to network-assisted cell change. That's a requirement there. As Pau has just pointed out, SGSN also has received IPv6 fixes. that would still go to the GGSN here. So and yeah, we had some problems with routing downlink traffic in case of intra-rack cell changes, exactly the cell changes that we added support for a little bit earlier, which had some problems. Osmo Msc, only 4 topics here made it to my list. SMS correctness fixes, more VTY commands for state introspection, so you can now have more insight into what's happening, what are the ongoing calls, what are the ongoing transactions, in which states are they. We have BSSAP, that's the A interface, correctness fixes in various messages, and rudimentary support for Msc pooling, which is well, I mentioned it when speaking about the BSC. It's this approach where a BSC is connected to multiple MSC, and there's some load sharing going on between those MSCs. And we have some very basic support in the MSC, so we can test the BSC, where we fully support pooling. Okay, that's sort of the quick and intense deep dive through the CNI, the Cellular Network Infrastructure projects. There's a couple of other projects, of course, in Osmocom, and at least on some of those, I can share what's been happening. On some others, I don't know, to be honest. But at least on those, some notes. We have the ICE1 USB hardware. That's the USB E1 interface, open source hardware with an FPGA-based approach by Sylvain, who's also here as TNT. So a lot of thanks for all his hard work on that. The hardware is completed and it's available for purchase, but of course it's open source hardware, so anyone can build it as they please. We also have firmware, gateway, and host software, currently supporting 1 of the 2 physical E1 ports in the device, not supporting 2 yet, but hasn't been an urgent need yet to do that. Yeah, as Sylvain says, gateway is also complete and supports 2 ports, so it's really just the firmware and host software that needs the update for 2 ports. The original driver for this hardware was called Osmo E1D, or is still called Osmo E1D. Since I was doing a lot of work on DADI last year, unrelated to Osmo E1 or ICE1 USB, at some point I thought, okay, let's try how hard it is to actually add a DADI driver. And DADI is the Digium asterisk hardware driver interface, I think is what the acronym means. So it's like the most popular driver interface for E1, T1, and telephony cards, like traditional POTS interface cards, like FXO, FXS cards. And yeah, it was actually rather easy. I'm not sure whether it was 1 or 2 days, but then it was done. And there's already at least 1 user beyond me, and it seems to work. So we have a working DADI driver for this hardware as well now, which means more support, of course. And that means asterisk and other applications or FreeSwitch or whatever that implement support for DADI cards, which are all PCI or PCIe cards. Without any changes to those applications, you can now also use Osmo E1. You can use ICE1 USB. With that. There's also a tool called Prbs Test for doing bit error rate testing. Basically connect 2 ports over loopback, and then it will send pseudorandom bit sequences into 1 port and receive them on the other port and do the comparison and the correlation to see how many bit errors there are. We also added support for the super channel, which is basically, you can say, channel bundling of E1 time slots. Which is interesting in terms of frame relay support in the GB interface, but is also interesting in terms of supporting some proprietary ABIS extensions by Ericsson. Yeah, we have some interrupt-based error reporting now. Details. Osmo RemSim, the remote SIM software suite. We have not all that many large changes, a couple of bug fixes, but it's pretty stable last year. We now have the RemSim client, which is the software that you normally would operate next to a modem. So basically, the part that receives commands from a phone or a modem and then sends it to a remote bank, a SIM bank with SIM slots. That one has, traditionally, there's what's called Osmo RemSim client ST2, supporting the SimTrace2 card emulation firmware. And the RemSim client shell is now a new, like mostly for test use client, which doesn't work with real hardware, but basically you can type in hex strings as APDUs into this RemSim shell. It will send it over the RemSim protocol to a remote SIM slot. The response will come back, so you can basically you can simulate what a GSM modem is doing in order to test the RemSim software suite. And likewise, there's yet another new client, which is an IFD handler. IFD handler is how PCSC calls drivers. So now you can basically plug a RemSim client software as a driver into your PCSC daemon, which means any random application that uses PCSC can use a remote SIM slot via Osmo RemSim now. Bank daemon is the part that runs in a SIM bank or next to the SIM banks, next to the slots. It has been extended to do regex matching of slots, which works around some problems where the reader names change after USB bus enumeration and so on. So with some regular expressions, this can now be made more reliable there. Operational improvement, let's say. Then we have an Osmo small hardware Git repository where we had various Osmo clock generator fixes. Unfortunately, we still don't have a working firmware yet, at least as far as I'm aware. Several people wanted to work on that, but then always got sidetracked over the years. There's an SRU clock breakout board, which is a small accessory for the Ericsson site integration unit, which is part of the Ericsson base station infrastructure. We have added various front panels for the 3U component carrier, for the clock generator, for the clock breakout, and for the E1 tracer, which I think I didn't mention yet. We also have, I think it was in 2020, we now have a dedicated circuit board for the Osmo E1 tracer, which is a passive E1 interface tracer that you can use to tap E1 interfaces, which is interesting if you want to reverse engineer some proprietary protocols on those interfaces. The NGFF breakout board has just received an update, version 3, mainly about longer 5G modems. So somehow the 5G modem manufacturers decided to make cards longer than the NGFF or M2 specification specifies. And we adjusted the card to the breakout board to accommodate such cards. We just received them last week, so they will soon be available. And of course, the open source hardware design is already committed and publicly available. Finally, PySim. Well, we had Python 3 migration, support for lots of additional files. These are just some examples of the files that can now be written on the SIM card. We support the new Sysmo iSIM SJA2, which is the previous card model was end of life. That's the current SIM card model that Sysmocom is selling. That meant it's an iSIM, so it has an IMS application in addition to the USIM application. IMS is required for Welte or voice over 5G. And so we had to add general support for iSIM cards and iSIM applications and some helpers for service tables and so on. The biggest new change that's happening right now is PySim Shell. That's a new program as part of the PySim software where you can interactively explore and modify SIM cards. Originally, PySim had just a couple of command line arguments, which is fine if there's like 5 different parameters you want to write on a card. But now, as we get more and more complex cards, it's not just SIM, it's also USIM and iSIM and probably HPSIM and maybe some other applications on the card. Each of those applications has hundreds of files. Each of those files have I don't know how many records with I don't know how many parameters inside. So we need a different way of exposing all this flexibility to the user, and an interactive shell for reading, writing, changing directories, decoding data, encoding data, authenticating with certain pins and so on, seemed like the only way how this can be handled properly. So that's ongoing work. The basic Python shell is already merged, but there's still lots of improvements happening and extensions at this point. Yeah, that brings me to the end of the list. So while all of you can think about what I forgot and bring that up in a minute or two, I'd like to sort of go back from all of these low-level details onto a more like slightly higher level, more abstract point of view. I think in, let's say, the first 10 years or so of Osmocom, Osmocom, I think, was started in 2010. OpenBSC was started in 2008. Before that, let's say the 2008 to 2018 timeframe was mostly about implementing functionality at all, like making the GSM network work at all, implementing the minimum necessary parts, then first implementing all of it together in OsmoNitB, then separating all the parts, implementing all the interfaces, breaking it out, but still very functionality oriented. And in the last 1-2 years, so particularly in 2020, we see a lot of movement into like going beyond mere functionality, but caring about performance. And performance doesn't mean like performance of the software, because 2G is so slow that in most cases it doesn't matter how efficient or inefficient your code is on a 2020 hardware, but performance in terms of network performance. So it's no longer sufficient that a feature works, but it's important that, like on a global scale, when you deploy it as a network with many cells, the overall call drop rate or the overall handover performance or whatever is optimized, and we care about this kind of performance. And that sort of shows that there's more impact now and more use from real world operators. If you're in a lab with one BTS, you don't care about mitigating interference with neighbor cells or achieving non-oscillating power control loops. That doesn't really matter to you. That's only something that matters to a real mobile operator with an actual deployment and larger deployments and so on. And that is what we are seeing now, that the focus shifts. It's no longer sufficient to worry about functionality, but it's we need to worry about the performance of the network in the field. Okay. And with that, I'm at the end of what I could think of. So if anyone still wants to add while we are on the recording, something that I forgot, some important thing that happened in, let's say, 1st of January 2020 to now in Osmocom, please speak up. I must have forgotten something, I'm sure. Okay, nobody wants to add it. No, go ahead. Yeah.
I'll just point out, because it was something that I worked on for a number of months last year, and with help of somebody kindly sending me a phone, we tracked down this bug in the SGSN with the encoding of the what was it? The radio access permissions. And I mean, it's covered there in the SGSN under various fixes, I suppose, but it was such a huge deal for a long time that there were these phones that just you connect them and then they operate fine for 30 seconds or so. And then once the TBF is gone, it will not establish it again, because the phone considered that it didn't have access to access the cell because it was hard to track down, because some phones weren't paying attention to the radio access permissions, and or they were interpreting it as whatever. I think it was the spec is that it's got 3 different parameters, but we had 0 or something in there, which some phones took as whatever. Anyway, that was it makes such a huge difference because all the phones now have got access to RAT in the cell, and there were various tickets about it, different people having had their own experience in some way or other, and it was fun for me because it was such a hard thing to track down, and it's such a one little bit in the STSN messages that made such a huge difference. Anyway, that's all.
Yeah, thanks for sharing that. Indeed, I saw it when I was doing the review, but yes, it's maybe a particularly important fix, but I tried not to look at all of the individual bug fixes. Otherwise, it would have exploded, of course, in terms of the number of topics to present. But yes, sometimes a small fix in the code can make a big difference, of course, to many users. No question, and I'm very happy that this got fixed. Trying to find it in the Git commit log now, but I was not successful to do this on the fly, basically. Okay. Has just been mentioned that Osmocom got a Wikipedia article last year. Yeah, I mean, it's just that, nobody really actively involved in the project cares a lot about PR. I think Osmocom has always been sort of the underdog of related projects, whereas, let's say, OpenBTS has always been very communicative with a book, I think, published at, I'm not sure which, like a printed book published somewhere, and in Wikipedia for a decade or so, Osmocom was, I mean, nobody outside the community bothered, nobody inside the community bothered. Everybody is busy working on code or documentation or deployments or whatever. But yeah, it's nice that somebody took the time to document what we do and what we are. Yeah, as Pau points out, there's also Osmo Modbus. Yes, I didn't mention that. Indeed, there's now a library implementing Modbus protocol around libosmocore. I'm sure there's many different things that I didn't mention. Of course, it's a summary. Just try to mention the most important ones. Okay, so before we stop the recording, maybe a slight outlook on what I think is going to happen this year in 2021. On the one hand side, sort of it continues what I mentioned before, more focus on network performance, less on, I mean, basically the assumption is that functionality is there and works, but now we, I mean, at least the assumption of users, but of course also from our side in general, I think we have the assumption that things work much better than they did many years ago. And we focus more on the performance and scalability of the network. Also, a lot more enterprise features. And with enterprise features, I mean things like network-assisted cell change, or maybe even packet-switched handover, or even inter-RAD handover at some point. So there's a lot of discussion about fairly high-end topics. We'll see, but I think in general that's the direction in which we move. There's also very likely that we will get GSM-R support, that's railway GSM, later this year, probably towards the end of the year. That includes full support for circuit switch data, which I personally have always been interested in very much. I mean, GSM-R as well, of course. But also beyond circuit switch data, support for these group calls and voice broadcast calls that exist in railway GSM. So that's likely going to happen. There's some chance to implement Megaco or H248, which is another protocol similar to MGCP in order to support media gateways with other protocols. And beyond that, I don't really have a clear sense of what exactly we will be implementing, but that's sort of the direction I think that things will be moving. We'll see how that goes. Hopefully, we will also get a chance to finally do more about the integration with Open5GS to have like a solid basis for operating not just 2G and 3G networks, or 4G networks, but like fully integrated networks going from basically across all the Gs. We'll see how that goes. Okay. With that, I'm going to stop the recording. Thanks everyone for listening to this OsmoDevCall number 2. Looking forward to seeing many people for the third OsmoDevCall in 2 weeks. And now we start the unstructured supplementary social event.